in the previous lecture we talked about areas, situations of areas, and a rederivation of the flux W equation, which states that the double integral of the flux is equal to the single integral of the variability. So this is the flux W equation. In the previous lecture, I derived it, and yeah. So for those who need a recap, flux is the change in the confidence, and variability is the change in the appearance with respect to time. So today's last lecture lesson, I'm gonna be using actual numerical methods to approximate characteristics. So if we're given a function of if we're describing one variable or one characteristic with respect to another or with respect to time, and we have some differential equation, how do we approximate the solution to that differential equation? And that's basically done via a method, a numerical method known as Euler's method. Euler's method. Most of you would probably pronounce this as Euler, but it's actually pronounced Euler. Likaw, not Euler. So Euler's method is a way to approximate a function given as initial nudge, delta x, and given an initial. So we have an initial value problem or initial boundary problem. Usually just an initial value problem. Y dot equals f of x y such that at a point x equals a, y is b. This is b, not a note. This is how we write an italicized b, like LaTeX. So given this initial value problem, like say y dot is equal to x plus 1, there. This, for example, and such that at x equals 2, y is 0, right? 2 is a root, right? Given this kind of initial value problem, we can use Euler's method to approximate y, given this, and some prescribed delta x, c. But c is usually better when it's very, very, very small. If it's like 0.000000000.1, that's a really good approximation for y. So we have some prescribed nudge or delta x to the function, and so yeah. So there are two formulas that we use for Euler's method, and so given. Alright, I'll write it here at the top. Given the initial value problem y dot equals f of x, y, x is a, y is b, and we have a prescribed nudge, c, nudge to the input, c. Okay, so it's basically like Newton's method. This method is like Newton's method, but Newton's method, we're finding roots or inputs or parts of the function wherein it's 0, or it's as close as we can get to 0. So for this one, x sub k plus 1 is equal to x sub k plus h. Well, I just want to note that h is basically delta x. H is equal to delta x. Okay, h and delta x are the same thing. So we have an initial x value plus h, and y sub k plus 1 is equal to y sub k. So we have an initial value for y plus h or delta x times f of x sub k, y sub k. So we input these values, we input x sub k and y sub k, our initial values, into the function, and then multiply it by that initial nudge, or that delta x. So I'll just write it here, plus delta x, f of x sub k, y sub k. There. This is Euler's method. This is a group of formulas you can use to approximate y and x given some initial value. So given this initial value problem. So in the context of this here, this is our first guess, or first y and x. So x sub 2 can be found via, well, x over here plus the prescribed delta. So a plus c. No, okay, don't misconstrue these two as the characteristics we know from the beginning. These two are arbitrary variables that are in no way related to what we discussed in the notation lecture, okay? These are two separate, different variables. We're gonna discuss that later on, when I'm done giving you guys a good discussion on what Euler's method is. Okay, so given our actual values over here, x sub 2, our second x is basically, or better approximation for x is just a plus c. And our better guess for y sub 2 is basically b plus h times f of a b. So we put a b into this function over here, f of x y. Put a b into there and multiply it by this delta xc. So that's actually c. So b plus c times f of a. That's our second guess. Okay, so how does this relate to our notation and the LGBTQ+ community? Notation. If we're describing one characteristic with another, let's say we're describing the choice with respect to time. So let's say that c is a function of time, and just write as y. So we have some function of t, y. So there, say this is t. We want to describe it with respect to time. So the decisions made over a certain interval, you guys know the drill. Okay. So we're describing with respect to time. Now, what if we're given some initial value problem? We're given some initial value problem. Y dot equals, well, let's say c plus t. C plus t. How do we solve this? Well, we can't really separate the variables. I don't want to separate the variables. We can definitely separate the variables and go, well, dy equals c plus t dt. There's definitely an analytical solution to this, which is something like E, Euler's number. But what if we want to approximate it numerically? Okay, so c y dot is equal to c plus t. Where y dot, I just want to know the y dot. I'm adopting Newton's notation. Y dot is just basically dy over dt, or the derivative of the function. So roughly speaking, this formula over here describes the rate of change of our decisions with respect to time. So this is basically this function over here describes our confidence. This describes confidence. So okay, so given some initial value, this is our initial value problem. C plus t. C is an independent variable. T is a dependent variable. It's a differential equation, for Christ's sakes. So so let's say that we're given some value that at t equals, well, let's say pi, c is equal to 0. Alright, so we need a function that satisfies this equation and satisfies these boundary conditions, and that our prescribed delta t, or h, is 0.01. Alright, given these conditions, let's approximate y, or let's approximate c. So using Euler's method, which is simply actually we in the book, in elementary differential equations, they express it in terms of differentials, but I'm just gonna go straight into the formulas, and give you guys the Rx sub 2, or T sub 2. T sub 2 is P sub 1 I plus our prescribed delta H. delta T or H 0.01. So I'm just gonna, yeah, it doesn't really affect the number much. It's actually an irrational number. Pi is an irrational number, so it's something like just pi plus 0.01. That's our value. So actually, if we say that pi is 3.14, all right, let's approximate pi to 3.14 or estimate it to 3.14. Or this would actually be 3.15. 3.15. That's your T2. And just assume that pi is 3.14. Or I can say 1. Let's do 1. So there's 3.151. That's pi. That's our T sub 2. And so we just use this in the formula so that we can obtain our C. C sub 2. This is our C sub 1. As we know, C sub 1 is our T sub 1. Okay. So that is B, which is this one. 0. It's actually 0. 0 plus 0.01 times our input. So we just put C and pi over here. So that's just pi. That's 0. Pi times 0.01. So using this over here, 141 times 0.01 is, it gives us 0.03141. And using these C sub 2, we can find C sub 3, we can find T sub 3. It just goes on and on. We can just keep approximating until we get a good value as we can estimate it, estimate this for as much as we want. We can get better successive approximations by making H smaller and smaller. Does that? So at T sub 2, C sub 2 is 0.03141. So it's a positive. If we assume that the positive domain of integers, positive domain of integers is male, and the negative domain of integers, or range actually, range of this is female, our specimen at T sub 2 is male. So yeah, I don't know actual values. Okay, so we know that at this C sub 0, so T sub 2, which is 3.151, C is 0.03141. So another one. Let's do another one. This time x squared. Let's try x squared, alright? So this time, let's describe appearance with respect to the choice. So this time, appearance is a function of the choice. So we have an initial value problem, y equals a squared plus c squared. Alright. And our initial values are, well, let's say at c, at c equals 2, a is -1. It's -6. And h, or our prescribed nudge, is 0.05. Alright, I actually want to leave this to you guys as an exercise, as I think it's going to be part of the homework for the course syllabus. If you guys don't want to if you guys want to answer this for yourselves, I suggest you guys pause, go to the course syllabus, answer on your own. But for the remaining time, I guess that's it. This is just, I'll leave this as an exercise for you guys since we're out of time. So for the next one, for next lecture, we're gonna discuss about behavior as temperature. So let's say the choice of an individual is determined by outside factors like thinking and seeing other people. So if he sees that that person is more feminine and likes it, starts being more feminine. So that's the thing. That's a behavior acting as temperature. It's all there in the course syllabus. After that, we're gonna start discussing conversion armaments 1 and 2. First one is trap conversion gas. Very important one. Yeah, it's a common theme in the femboy community. Trap conversion gas, like converting people using gas. So that's that for this lecture. Let's see you guys in the next week.